Let's start the class. And today we are continuing designing algorithms. So the previous time, this was one-to-one mapping algorithm that we discussed. And we discussed about the different approaches that you can take it, and you want to take the most efficient algorithm. So here we are continuing the same things by, again, considering different approaches that we can take for each of these problems, and see which one is the more efficient one that we can take. And these are, again, as I mentioned, if you go for Geek4Geeks or LeetCode or others, you will see that they are trying for this problem. This is the maybe the easier way to implement, and maybe less efficient, and then there are more efficient algorithms. So this is the type of thing that we always do. Now, and also these are the nice problems. Again, the view is important, that you need to have the right view on the problem. Otherwise, it might be, even the implementation might be hard if you don't have the right view. Good. Now, let's talk about this problem. So this one is the celebrity problem. This is actually a nice problem. So a celebrity among n persons is the person that is known by everyone. So this is a celebrity. So it is a celebrity person. So to say we have a directed graph. I mean, that this person A, B. So this was the meaning of this, means that A knows B. So A directed to B, it means that A knows B. A celebrity, a person, is a person that it's everyone else knows this person, but this person does not know anyone. So there is no such edge from this guy too. Is the definition clear? Everyone knows this person does not know anyone. Celebrity, I don't know, is it a good definition or bad definition? But anyhow, this is the definition. I mean, like, I don't say a good person or bad person, I don't know. But this is a definition. Or a good concept or bad concept, maybe not good person or bad person. Good. So this is a definition. And the question is that you are given, okay. So you want to ask people some questions. And by this asking, you want to, with the minimum number of questions, see whether this community actually has a celebrity or not. Good. There are n people. Here, we want to minimize the number of questions. You can think about this one. So we can consider this one as a query. So you can have essentially, this is algorithm which are called sublinear algorithms. The sublinear algorithms, so here you can think about this one, that you have a matrix that essentially, like from I to J is 1 if I knows J. This is a matrix. But in the sublinear algorithm, this is actually a class of algorithm, you don't need to try to read the whole matrix. You try to, because what is the size of, if we have n, what is the important parameter here? N is the number of people. Good. So if you have n persons here, so the size of this table would be n square. And the question is that we may not want to read the whole n square. We will try to read it as little as possible and decide whether there is a celebrity or not. So this is the type of algorithm. It is called sublinear. Why sublinear? Because here, in some sense, the size of the input is order n square. Because this is the size of the matrix. So instead of n square that we will go and check everything, we don't want to read everything. We want to do it as little as possible and find that celebrity. So in some sense, when you are asking the minimum number of questions, means that the minimum number of queries to this paper, to this matrix. This is the minimum number of queries. That you want to do it in this table. Good. Is the problem clear? The people on Zoom, is it clear?
Yes.
Good. Now, the question is that what would be the, so here, I mean, the number of pairs here, of course, we have n choose 2, we have n persons, so we can have n choose 2 pairs, and which is equal to n times n minus 1 over 2. And this is both ways. So if you consider, this is a directed graph in some sense. So it may be the case that A knows B, but B may or may not know A. That we don't know. So in some sense would be 2 times that, which would be n times n minus 1. In some sense, why it is n minus 1? Because we are just excluding this, like the, so I knows I is irrelevant. So if we remove that, n times n minus 1 is exactly the size of this matrix minus this, if you just remove this diagonal. Good. Now, so how should we proceed essentially? Let's say this one, if we want to check whether one person, if we know a particular person, we want to check whether this person is celebrity or not, then what do we do? Yeah? Okay, talk a bit louder.
If like that person doesn't have any ID from 8 to like from 6, there shouldn't be anything coming up.
Yes. So the check, I mean, if you want to check if someone is celebrity or not, it's essentially you are doing this one. So you need to ask from everyone else, asking whether they know this person. How many questions do we need to do that? N minus 1. And also we should ask whether this person, from this person, whether this person knows anyone else or not. Good? Yes?
Yeah.
Can non-celebrities know each other?
So what is that?
Can non-celebrities know each other, or do they only know the celebrity?
Okay, so one question. So non-celebrity, they can whether they can know each other or not? Yes, they can know each other. So here, like as I mentioned, n minus 1, we need to mention that, make sure that everyone knows this person, and plus n minus 1 to make sure that this person does not know any other. So one other question: how many celebrities can we have here? Good. So how many? So the question is that how many celebrities can we have instead of n people? Yeah.
N minus 1.
Is it n minus 1? So we have n people. How many celebrities can we have?
Isn't it at most 1?
Yeah, at most 1. You cannot have 2 because just consider these 2 people, celebrities. If one of them knows the other one, then that person is not celebrity. Good. So if there are 2 celebrities, you just consider this A and B. So what is the relation between A and B? If one of them knows each other, then that person is not celebrity. At the same time, if these guys celebrities, it means that everyone else should know them. So this is a contradiction. So you cannot have more than 1 celebrity actually. So at most 1 celebrity we can have. And the question is that how many questions we have it. Now, checking that someone is celebrity or not, that is. But the question is that we don't know. I mean, there are n people, there are at most one of them. We want to find that one. Possibly. It might be the case there is no celebrity in the thing, at most one. So the question is that what would be our strategy to do that? Of course, one idea is to go and check the whole table that we have it here. To just go and check the whole table. This is order n square. Of course, we want to do it better than n square. Because if you see the whole table, then we can see that. I mean, just check for each row of the, essentially we can do this one. You can consider each person. For each person, just run this algorithm, just ask these questions, this number of questions. So, I mean, it would be n times order, I don't know, 2n minus 2, which is order n square. So that is not a very good running time. So the question is that this is exactly the right view, the correct view. So if you don't see that, this problem is not that easy because you need to see that to find this person. The question is that how can we design an algorithm which is actually works better in this case? Any ideas? Yeah.
You could move through each row until you find a 0, and then you know that the second entry or the J in that is not a celebrity. Because not everyone knows J.
Yeah, but when we consider this algorithm, we consider the algorithms. So if you want to start from some top and then you will go on such a, you will find the first one that is 0. The issue is that you should consider the worst case. The worst case is that it might be all of them 1 and you need to go to essentially the whole matrix. So we generally talk about the worst case analysis because of several reasons. First, I mean, there are best cases. I think we mentioned it. The best case, I mean, it does not, maybe that best case almost rarely happens. Even there are average cases. And for that, for example, there is a smooth analysis or this type of thing that the people have considered it. But even the average is not quite well defined. It might be like, in the practice, it might be the case that actually this average case, maybe random case or something that does not happen. So we cannot necessarily just go and talk about the random case. We need to talk about like our average case. Generally, it's easier to just consider the worst case. So in the worst case, that can be n square. Let me give you some hint. So if, let's say we are, again, this is exactly the type of, again, thing that in the interview, you will say that, okay, n square, I can do that. Okay, can we do anything better? The question is this one. Consider like one question. When we ask one question, what information do we get out of this? Yeah.
We could ask if they know anyone else, if they know someone else that they know. So we can know that.
So can you talk a bit louder?
We could ask if they know anyone else. For each guy, ask if they know anyone else. If they know anyone else, they cannot be disability.
But okay, so the set of questions that we can have only say that whether A knows B or only we know only we can ask whether A knows B or not. We cannot say whether you know anyone else. Why? Because they are corresponding to queries of this table. In this table, if I want to see whether this person knows everyone, I need to see the whole row or the whole column. Yeah?
We can eliminate at least one person from whether or not they're celebrities. Because if A knows B, then A is not a celebrity. If A doesn't know B, then B is not a celebrity because somebody doesn't know them.
Exactly. So this is actually this is the view that you should consider. So if you consider A and B here, so I'm just asking from A to B, whether A knows B or not. If A knows B, then what's the meaning of that? A is not celebrity. And if A does not know B, then what's the meaning of that? B is not celebrity. So by just one question, I ask A, do you know, I'm asking A whether you know B or not. And then if he says yes, it means that A is not. Because a celebrity, by definition, is the one that everyone knows that person, and this person does not know anyone else. And if A does not know B, it means that B is not celebrity, because that doesn't. Good. Now, it means that with one question, we can eliminate one of these guys. So I have n person at the beginning. I want to have one candidate at the end. How many questions should I ask? Yeah, n minus 1. So you can ask, essentially take the first two guys, A and B, the first two guys. And one of them knows, or depending on whether this guy say yes or no, you may remove essentially one of these guys. You see this. So you know that whether, depending whether A knows B or not, like the first person or second person, one of them will be essentially eliminated. Then the winner, in some sense, go now next time with the third person, and you will do that. After n minus 1 question, n minus 1, I'm coming with at most one person. So it might be the case that you see the first person and second person, the first one wins. Then with between first and third one, again first one wins. By wins means that does not get eliminated, and so on and so forth. So it might be the case that the first guy is actually the one that wins or survives the last. I need n minus 1 questions. Then after that, what should I do? Yeah.
Check if he's a celebrity.
Yeah. So after that, so I have essentially this one. So I have n minus 1 questions to eliminate n minus 1. Then after that, I have one candidate at most. I need to check whether this candidate is a celebrity or not. So I need to do this n minus 1 plus n minus 1. So the total would be, so I need to have n minus 1 to eliminate, to reach only one candidate. And then I need to check, this was essentially the time to check whether a person is a celebrity or not. So the total of these things together it becomes 3n minus 3. Good. Now, can we do a little bit more efficient than that? So we have 3n minus 3 questions that I need to ask to make sure whether there is a celebrity or not, and check that that person actually exists. Yeah.
Why is it n minus 1 plus n minus 1 to go through?
I mean, because that's the thing, that n minus 1, you need to ask this person whether everyone knows this person, n minus 1 question, and that this person should not know anyone else, n minus 1 questions.
Aren't you only asking if this person knows this one other person?
What's that?
I thought you were only asking if A knows B, so it's like 1, right?
Yes, but then you need to ask also B whether knows A or not. Because a celebrity, again, by definition, everyone should know this person, and this person should not know anyone else.
So you go through A knows B and B knows A. Right?
So we have 2n minus 2 there, and then n minus 1 here to find this person. But the question is that, can we do a little bit better than this? Do you have any ideas? Anyone on Zoom? Do you have a question? Do you have ideas? Yeah.
Got a question. Why can't we ask if A knows B and B knows A at the same time?
Because again, these are two different matrices. So this is IJ, and the other one is JI. So these are two different places in the matrix. you see, we have a given matrix and we want to read this big data, and we want to get sublinear algorithm. But why? Because the size of this guy is n to the 2 plus order n to the 2, which is order m. So say m is the size of this matrix. I want to do it somehow. This one, if we are doing it, we are doing square root of m. If m is the size of the matrix, so far the one that we are doing 3n minus 3, it is square root of m. This algorithm is called sublinear algorithms. And there's a lot of work. So in some sense, this is actually a good case that we can, with certainty, we can answer it. But there are several cases that we might not be able to get it with certainty. And we say that, okay, probabilistically we get some answer. With some probability, I can read some places. Some places actually you may read only a constant number of places in this table and give me the answer. Yeah.
So when we go to the structure, whichever one you make, why don't we know whether that? Why can't it be the? Why do we know for certain the celebrity?
Yeah, because I mean, it might be the case that, I mean, this guy that is the candidate, like you are, as I mentioned, you can start with a person like 1, then person 2, 3, and then you will do it 1 and 2, and the winner goes with 3, and so on and so forth. It might be the case that when you go to n minus 1 at n, so far just essentially the n minus 1, that this was the guy that was winner previous one. Between n minus 1 and n minus 2, this guy essentially, actually even simpler than that. It might be the case that when you consider n minus 1 and n, in this case, n is the winner. Good. N is the winner. You don't have that much information about n. This is the only, but actually we have a little bit of information. What is the information? At least we have asked one question. So the last person, the person who survived, we have asked one question. Either we ask whether he knows someone, or that person, or someone else knows this one. Yeah.
Is there a way to format these sort of eliminations such that each person gets asked roughly the same? The winner gets asked the most questions.
Not clear. Because you might be in bad luck, and the last person essentially is the one that you are.
Like pair them up and then branches out a binary tree.
Good. So yeah, so that's the way, essentially that's the idea. So if you want to just save here 3n minus, so here, I mean, if we just use this algorithm, we know that from this last guy, we have asked at least one question, correct? Because we have at least one question, so here we have 3n minus 3, we can actually make it 3n minus, because this information that we know, we cannot ask this question. We can avoid to ask it. But as he mentioned, actually, we can do it like maybe more balanced way, such that the first 1 and 2, this is some kind of binary trees, essentially, we can do it here. So we can have it like, for example, this person, like the, maybe instead of this one, let me actually, yes. So we might be able to do this one, 1, 2, 3, 4, n. And you might be able to do something like this. First these two guys, then these guys, then these guys, and then one of them will be eliminated. And then the winners, they are coming together, and so on. In this case, actually, you can make sure that each person has been asked log n times. And this log n information is the one that you don't need to repeat. So you may save actually this log n. So the question is that what is the best bound? That's the interesting thing. You can think more about it. Can we do even better than that? I think here we say that 3n minus log n, but can we do anything better than that? So that is some assigned thing that you can think about it. Good. So let's go there. I think you can actually see the code of that in the in the book. Just go, and I think that is one of the things. It would be good actually if you go and try to code them up in Python or in C++. C++ also would be good. Both of them would be, if you can write both of them, that would be good. C++ using STL actually would be very easy to code it up. Good. Now let's see another important problem. So evaluating a polynomial. So you are given a polynomial. So these are the real numbers, a1, a2, an. So these are like you can say float or double in C++ or Python. So these are the things that are given to you, and a real number x is also given to you. You want to see what is the Pn of x. What is the Pn of x? Is that, I mean, Pn of x is that an to the x, and an minus 1 to the x, n minus 1, and so on and so forth. So you want, this is essentially Pn of x. You want to evaluate it. So the question is that you want to evaluate this Pn of x on this given point x that is given to you. So like you can see that actually x0 is given to you, and you want to compute Pn of x0. I just want to say, I mean, there are this new live that we had it. I think it was interesting yesterday about potentials of e-commerce. That's a good one. You can go and take a look at it. That's the nice one, that you have some information about advertisements, auctions. These are complicated things. Good. So how can we compute Pn of x0?
You could say recursively, but you could compute P of n minus 1x, and then you get the result that you multiply x by x to the power n minus 1.
Yeah, so I think one would be something like this. So let's, again, this is the first view, and then second view, and the third view. It becomes smarter and smarter. So one is this one. So, okay, we can use induction. So this is, we define Pn minus 1 of x, which is a of these guys. Say that we have essentially computed this polynomial by degree n minus 1, and then we want to compute it for degree n. Good. Now, one way to do that is and we want to see how many multiplications and how many additions we need to do that. Good. So let's, I mean, say if we have this Pn minus, like Pn minus 1 of x, then how many more additions and multiplications we need to do that? Yeah.
If you use the power function in STL, I think it computes the power recursively, so it's log and multiplication.
Yeah, but okay. So, but yeah. So let's do it a bit more naive than that. So we need to compute x to the n, correct? For this, how many? I mean, operations do we need it? I mean, if we do it naively, we need n minus 1 multiplications, correct? Because you need to have x n minus 1. As you mentioned, we can do it actually recursively. We can do it powers of 2, and there we can do it actually log n multiplications. After that, what else do we need? So we need to also multiply it by +1 multiplication. We have it. And then after that, you have one addition as well. So here, I mean, if we do it naively, we have essentially n multiplications and 1 addition. If we do it a bit more smartly, maybe we have it log n plus 1. multiplications. This plus 1 because of an, that we need to have it an times that. And then, so log n plus 1 and then 1 additions. That's one way that we can do it. Now, if you do it recursively, so the number of additions is not bad. So the number of additions would be something like, because it is A0, the number of additions would be n total. So the total additions so total additions would be total integer additions. And the total multiplications would be the sum of the numbers n plus n minus 1 plus 1. That's this sum actually is n times n plus 1 over 2. This is the multiplication. So we have n addition or this multiplication. Actually, if you do it a bit more smarter, maybe log n plus 1, then you have the sum of this log n things, which would be essentially log n times n log n. So that's one way that we can. Now let's do it a little. So that would be one way. This is number. Now, yeah.
So how are we reaching log n? One more.
What is that?
How are we reaching log n multiplication?
So essentially, for example, if you want to get x to the 4, what can you do? You can just do, you can multiply x times x, then it would be x to the 2, then x to the 2 times x to the 2. That would be 6. So this is the general idea. If you actually see the binary representation of these guys, so if you want to get it some n, so the question is that how can we do it log n, essentially? Multiplication. So if you write n as a binary number, so it is 1 0 0 1 0 1, then it means that you need essentially to create this one, you only need to multiply, I don't know, here x to the 0, then x to the 1, then x to the 2, x to the 3, and x to the 3. X to the 2, 3, and 4. So you just essentially, if you see the binary representation of n, you will just go there and you just multiply only. So you have x, then x to the 2, x to the 4, and you just multiply those that are in the binary representation of n. These are ones, you just multiply those guys. So in particular here, you just multiply x and x to the 4. And you have at most log n powers of x that you need to compute. Yeah.
The total number of multiplications is n plus n minus 1 down to 1, right?
Yes. I mean, if you want to do it naively, if you want to do it this way, would be log n plus 1 plus log n minus 1 plus 1 and so forth. That would be the total would be n log n, order n log n.
Okay, it's because you wrote n plus n. Yeah, you wrote n plus 1 instead of n plus n minus.
What is that?
Uniform.
So where did I mention?
n plus 1.
Oh, sorry, yes. Sorry. This is n minus 1, yeah. Good. So that's one way. Now let's clean it and then go another way. We can actually do it smarter than this. So, what would be the smarter thing? We said that we are using a stronger induction hypothesis. And again, these are the base case are easy. I don't talk about the base case. You can check it yourself. So we are assuming that we know the solution Pn of x, correct? Pn minus 1 of x. That was the assumption that we had. But say, assume that in addition of that, also I have xn. x to the n. Good. So when we do this a stronger induction, we need to make sure that in the next step also we have both of these values. Say if I have this number and this number, then how many additions and how many multiplications I need to do now? Yeah.
For each new term, you need 2 new multiplications and 1 addition.
Yes. So here that actually I'm saving because I have this one. I have also xn, correct? So I can just add multiply an by xn. So here actually, I mean, assume that you have also this one xn minus 1 here. So here I have also, so I have not only I have this one, but also I have xn minus 1. So what do? I need to multiply an by, okay, first I need to get xn. To get the xn, I need 1 multiplications. So that would be 1. And then I need to do it times also this one. So let me write it this way. So we have an times x times xn minus 1. I have 2 multiplications here. And then I have what? How many additions do I need? 1 additions, I have it. Also, I mean, one other thing. When I go there, now I have Pn of x. But also in addition, I have also xn, because I have also computed. Xn also I have computed. So induction works because not only I need to have Pn of x, but also I need to have xn as well. But xn also has been computed because you have multiplied x by xn minus 1, so you have computed. So now how many additions, how many multiplications in total? Okay.
0 multiplications.
Yeah, we have 2n multiplications in total and n additions. So this is the total. Good. So it's better than n log n multiplication that we had, and we had n additions. Yeah.
So for the power of n minus 1, when did you calculate that?
So that is something that is inductively we have to it. I mean, in some sense, you can think about it. This is a function. Like if you do it in Python, you can actually return a pair. So the function that you will call it recursively not only returns Pn of x, but also returns x to the n. Then that function, you will get it, you will compute it, and you will return it 1. And again, so this induction actually is very similar to recursive algorithm. So whenever you have induction, you can turn it into an algorithm by just writing a recursive algorithm. And you read about, have been taught about recursive algorithm in previous courses, correct? Good. Can we do now? We gain 2n addition, 2n multiplications and n additions. Can we do a little bit even better than that? More efficiently, even more efficient than that is this one. So let's define p prime. P prime is because of the derivative. That's the reason that I put it p prime. P prime of n minus 1 of x. It is an to the x to the n minus 1. So before, in the Pn of x, we had it an times x to the n. Here we have Pn an times x to the n minus 1. Plus a to the n minus 1 times x to the n minus 2. And so on so forth to a1. Here, essentially, we have a1 x to the 0 in some sense. So we have a to the 1 to the x to the 0. And then a0 I mean, A0 has been essentially removed from this consideration. And this is 1 as well. So we can have it. So this is somehow the derivative of this. Assume that we have this formula. Yeah.
So why do you multiply it by n? So let's say a sub n times n times x to the power n.
Sorry, what is n?
Because like when you take the derivative of x to the power n.
Yeah. No, I'm saying that, I mean, it is the intuition comes from that. It is not derivative. It's not. It is p prime of. Yes. Thanks for the clarification. It is, the intuition comes from it, but it's nothing. Good. Now, if we have this formula, if we have this one, then actually I only need one multiplication and one addition. Why? I just multiply this formula by x, and then I will add it A0 to that. Good. So, so is it clear? So if you have a Pn minus 1, I mean, I have just multiplied that one with x and then plus A0, that gives me the formula. Good. Now, what would be the essentially so the whole things to evaluate that one, actually we can do it with such a simple algorithm. So what do? I think this is the input. So again, what is the input? I'm just reading these coefficients from the input and also the real number x. So the first n is given to me, and then these numbers, and then x. How do I compute the value of the polynomial at x? I will do this one. I will put p equal to an. Then for I equal to 1 to n, I will just make sure that p is equal to x times p plus an minus 1. So what will happen? Let's see, what does it do? So first it computes an. Good. Then what do? I will just multiply this one. So I have x times an minus 1 plus an minus 1. Then I will just multiply everything by x. And I will add it an minus 2. So how that would be essentially x to the 2 times an minus, sorry, this is everything is plus. X times n minus 1, sorry, x an minus 1 plus an minus 2. Good. So on and so forth. I just do it n multiplication. That is the whole algorithm. N multiplications, n additions, and n multiplications, because we have a 4 of n loops. 1 is here and 1. Is it clear, everyone? So people on Zoom, is it clear for you as well?
Yeah.
You see, this is the one that I mentioned to you. If you don't consider it, if you don't consider it, sometime, if you do it the correct way, not all the time, but sometimes if you do it the correct way, not only it would be more efficient, but also it would be much simpler to implement. You see, the whole thing, if I want to do it the previous approaches, I need to return essentially 2 numbers, etc. But here, I need to do it recursive as well. That's probably the easiest way to do that. Here at the end, of course, I can also write this one recursive, but at the end, this is just 3 lines of code. The most efficient way and 3 lines of code. This often happens for these other problems that you are seeing. As I mentioned, for this lead code or HackerRank or others. But if you do it the correct way, Git for Geeks, then the implementation actually would be even simpler. Of course, then coming to that simpler way is not that easy. You need to really think about it. The first solution seems much easier, but coding up the last one is actually even easier than that. Clear? So this one I wanted to emphasize on that. This is about the strengthening of the induction hypothesis. That's important. What are the strengthening of the induction hypothesis? So sometimes we want to, this is the typical things that we are doing. We say that, okay, from P of less than N, we want to imply P of N. That's it. The induction that we have mentioned. It for everything, we assume that it is correct for base case and for everything less than N, and we want to get it for N. Sometimes we have another assumption Q as well. Now, what do we want to say? We want to say that if we have P and Q, so what was P and Q like in that previous case, that the example that we mentioned? We said that we not only we have Pn minus 1 of X, but also we have X to the N, or X to the N minus 1. We are having P and Q less than N, that implies N. That sometimes is much easier to do that. However, whenever you are doing that, you need to be careful that when you do, this is not enough. You also need to actually show a stronger thing. P and Q less than N implies P and Q for N. Both of them, not only P, but also Q as well. Good. So this is important that you need to do that. This is a common error that you may try to do it P and Q, and then you get P, and you don't prove that Q also can be obtained for N. In that case, so here, for example, when we have it Pn minus 1 of X and X to the N minus 1, you should say that, okay, we have Pn. Also, you should say that also I have X to the N as well. We will see another example here. These are some common errors for induction that you can actually see in the section 5.11 of this Introduction to Algorithmic Creative Approach by UDI members. That would be good actually to read. Yes?
How do you prove Q in the previous problem?
So in the previous problem, if you remember, we had, the first case, we had it Pn minus 1 of X, and we said that we also have X to the N minus 1. Remember? This is a Q statement. So then it means that we should have Pn of X, and also we should have Xn. This is Q of N. That's the thing that we need. We will see another example here. So this is actually a nice problem as well. So what is the problem? So you are given a sequence x1, x2, and xn of real numbers. They are not necessarily positive. You want to find a consecutive subsequence of this. So you are given a sequence. You want to find a consecutive subsequence. So this should be consecutive subsequence It means that you start from xi and you will go to xj, such that some of these guys, so it means that xi plus 1 plus xi plus 2 and so forth to xj, the sum is maximum over all subsequences of consecutive elements. Good. So let's see what will happen. So like, for example, consider this sequence, correct? So if we are considering this one, what is the sum of these guys? 0.5. Right? What about the sum of these guys? That is -2. So again, I mean, what is the sum of the whole things? What was that? Yeah, something like this. I mean, you can compute it. So you can consider also the whole thing. So among all these consecutive sequences, we need to find the one that has the maximum sum. And the maximum sum here is what? In this case, actually, this is the maximum sum. If you consider if you consider this guy, -1, 1.5, -1, and 3, then the sum would be 3.5, and that's max. Is the problem clear? So people at Zoom, do you see that? Is it clear, the problem?
Yeah.
Good. Okay, so let's start with the first look. Again, first look, second look, and the third. So the first look, if you want to compute for a sequence, so again, what is the input? The input is n, and then the sequence n numbers that you are reading. What would be a naive way to solve this problem? Yeah.
We start a sequences that begin at 2, and then we compute that the sum, then we move on to 3, 1.5, like what was given.
Yeah, but I'm saying that, what about in general way? So a sequence of length n is given to you. How do you compute it?
We start a sequences of 1, then that begin at first element.
Yeah, I mean, you can do it actually even simpler than that. So you know that, I mean, if this is the sequence is given to you, so I will call it, like, for example, I think here is A1 to A2 to AN. So you can essentially have some start I, some end J. So how many I and J can we have? So, I mean, essentially, you have n numbers. From n numbers, you want to do 2 numbers. So n choose 2 numbers for I and J, and then I have order n as well to compute the sum. Correct? So I will say, what is the beginning? What is the end? N choices, n, and then sum it up. Would be n. What would be the running time of this? It is NQ. Can we make this one a little bit more efficient to get it n square? Yeah.
Dynamic programming.
What's that?
Dynamic programming. Like.
No, I mean, give a simple algorithm. Yes, you can, I mean, use a dynamic program, but I want to have it simpler algorithm actually.
For each I to J, you can save that and use that to compute I to J.
Yeah. So you can do it actually n square easier. So you have essentially you are just choosing the first point. So how many points that we can be the first point? So how many choices do we have for the first point I? N choice, correct? Okay. So I will say that this is A1. So for A1, I will do this one. So I don't choose J and then, so this one that was inefficient because I choose I and then J, N choices, and then compute this one. Just sum it up between I and J. That would be N and Q. How can I do it a bit more efficiently? I can just compute A1. Then J, I don't fix J. So in some sense, I say, okay, this is the first A1. Then I will compute A1 plus A2. Then I will compute A1 plus A2 plus A3, and so on and so forth. So with a start of I will compute all of these subsequences that are starting with I. How many of them are there? How many subsequences, consecutive subsequences starting with I? At most order n, correct? How much does it take for me to compute all of them?
Constant for each. So
Constant for each, because I will start with A1 or AI essentially. Then I will add it AI plus 1. This is the first. Then AI plus 2, AI plus 3. So how there are order n choices, I also for each of them I'm spending only constant things. So in some sense, I don't need to have these n choices of J anymore. When I compute this sum, I also compute all of these guys. So here the running time would be what? Would be n squared. Because I have I choices for n and then n sum. Yeah. What's that? Exactly. So J would be always the last element that I will add. So whenever I add a guy, that's exactly the J. So in some sense, this idea of that I will consider I and J and then you compute this one, it was very redundant. I didn't need to do that. I just add one more and that's actually J. One more, that's a J. One more. So this, the running time would be n squared, and this is n to the 3. This is the naive algorithm. So we got first n cube, then n square. Now we want to see, can we do better than that? Of course. So for this algorithm, one may think about the previous, like the first algorithm that we mentioned. That algorithm was sublinear. If the size of the matrix was m, the running time that we had it, the number of questions was square root of m. As I mentioned, generally that does not happen. That for that problem we were lucky. Or if we do it, we get with some probability the correct answer. Not always. Generally for this problem, so I want to say that in this problem, we need to at least order n to find the maximum. Why? Yeah.
because you need to compute the maximum and that's for
No. So this is like essentially, we have a few approaches of one proof. I mean, one proof is essentially by induction that we have done. Then we want to say that we need at least this number of operations. This is the proof by contradiction. Why? Say that, okay, I say if I read less than n from the input, it means that one of these numbers, I should not read it. Correct? But that number by itself might be infinity. So if I have not read that particular number, then I might be in a very bad shape. Because that number by itself, maybe everything is negative, only that number is positive, and that positive is infinity, a very large number. So you really need to read all these numbers. All these numbers are important. So at least you need to read the whole input. And this is actually, in this case, even you cannot give any approximation for the problem. Because again, it might be the case that everything else is 0, except that particular number that you didn't read. And so if you get even 1 versus 0, 1 over 0 is infinity. So you cannot have even any approximation algorithm if you don't read numbers. Does it make sense? So, okay, we need order n. So as I mentioned, lots of problems actually we need, and this is the one that we are using, we need omega n running time. This is the part that, so we say order n to the 2 or order n to the 3. But here we say that it is omega n needed. Good. Okay, so let's now go to the algorithm. How can we do order n? What is the greedy algorithm?
The next number is positive, add insert. The next number is negative.
No, but you need to prove that it works. That is also important. So let's discuss this one. So you see, we have, let me just do these things. Oh, what is happening? Your map is, what? Google Map is did come. Okay. Let me finish it. Good. So let's write these ones, see what will happen. So we have here x1, x2, x3, and so on. x4, and so on. Good. Let's do this one. So we try to do it by induction. If the length of the string is 1, then we can just solve the problem. Just see whether, if that number is 0, if that number is positive or 0, then we can report that number. If that number is minus, then the empty, actually the solution would be just empty, like null essentially, because that would be 0, is better than that. Good. Now, let's go for x1 to x2. So, okay, now what do we do with x1 and x2? You have say computed the best solution so far. So you have computed the best solution so far. If x1 was the solution, say, and then you will come and read x2. If x2 is positive, then what do? You will add to previous. The problem appears when x to the 2 is negative. Then in this case, what do we need to do? What was that?
Ignore it.
Yeah, essentially the solution would be this. So we are coming to here, but the solution was x1 essentially. Good. Now we will go to x to the 3 essentially here. So again, this solution was x1 here. So here, x to the 3. Now what will happen? So the solution that we have is, say, x to the 2 was negative. Then, of course, now the solution, it might be the case that x to the 3 by itself is what? Is positive. Say, for example, x to the 2 was here, was 5, correct? x2 was, I don't know, maybe minus 10. Good. Then I'm reading x3. x to the 3 is, say x3 is, say 3 in this case. Good. So what will happen in the, so that if you consider these cases so far, so here when we have x, this was the first, when we had it the first things, that was the solution. When we had the 2 of them, the solution was still this case. When we have x1, x2, and 3, what is the solution? What is the solution?
If you add x3, that doesn't construct a subsequence, right?
Yes, but I mean, in this case, still the solution is x1, correct? So far is x1. Now say that I'm going there and this one is 4. So one idea for induction is that, okay, I will keep the maximum subsequence that I had it so far. Good? That I will keep it. But here, and of course, all of them, when I came there, I knew that from I to j, from 1 to 1, that was the solution. Here, I'm coming to x4. What is the solution in this case? Is it 12? Where did you get 12? What is that?
Okay, so that's 9.
No, why? No, it should be consecutive subsequence. It is not consecutive. So if you want to do that, then you should have -10. If you have -10, it would be, so you can 5 plus -10 would be -5 plus 3, -2 plus 4 would be -1. So it's not a good solution. However, I can just take this solution. Good. What is this solution? Is 7, correct? So what is the idea? The idea is that, I mean, this is the induction hypothesis. Yes, I need to see what is the best solution that I had it so far. However, that is not enough. In this case, that was not enough for me. I needed also find the consecutive subsequence that is ending to the last element. If I knew that, so I needed actually two sum to keep it. One is the one that I had it so far, the best solution overall, the best global one. I need also another solution. The best solution, the best sequence that is ending at the last element. Good. Is it clear? So here I needed to keep also x1. Also, I needed to see the previous solution that ending at here was x3 itself. Now I will consider x4. I will do this one. I will do, okay, either the global solution. So I need to, so this is essentially, this is P, this is Q that we discussed. So I have both P and Q here. Good. P is that it says, what is the global solution that I had it so far? The global solution. The other one is the solution, the maximum solution that ends at last element. Now, I will read the other one, x4 here. What do? I will say, okay, I had some global solution that I need to compute it. I will add this x4 to the largest sequence that is ending by x3, because that I can add it. I will add 4 to 3, it becomes 7. Okay, now it becomes 7. So it means that this is now better than the global solution that I had it 5. So now my global solution becomes this one. What about the maximum sum that ending the last element would be this? So in that case, actually, both of them become 7. So let's say there is one other element here. This is x5. Now go to x5. And then x5 is become -10. In this case, actually, what will happen? Now I will come to x5. Okay, x5, I had 7 here. If I want to add this guy to this guy, it would be -3. So it is not a good solution. So again, I will keep this solution as my main solution. So this is my main solution. Now I need to say what is the maximum sequence that ending at x10. What is that? At x5. x3 plus x4 plus x5 would be what? That would be -3. Instead, I can just say empty set. Don't do anything. That would be 0. So as you will see, at each of them, essentially, I only need order constants. I will just do one simple additions and multiplications, and I will do that. So this algorithm, actually, the running time of this is order. because I'm just reading it either at any time. What do? Either I will update my maximum solution or not. At the same time, also I'm updating the maximum sum that ending or my last element or last current element. Both of them takes only order 1, just some comparison, order constant. So in order 1, I need to do it, and there are n would be order n. Good. So that's essentially a strengthening induction, as I mentioned. When we do P and Q, we need to compute both of them for the next step. And then we can solve this problem.